All right. Hey, everybody. So in this video, I want to talk through what I'm calling an interesting example. That's an interesting set S and a couple of collections of open covers, script F. So the set S that I'm interested in is the set from 0 to 10. Notice it is half open, half closed. So it contains the number 0, but it does not contain the number 10. And I'm going to set up, again, 3 different open covers on the set S. And to keep it interesting, I'm going to make all of these open covers. I'm going to make them all infinite open covers, and then we can discuss whether or not they admit finite subcovers. So let's take a look. Okay, here's our first example. I've drawn a picture on the right here that includes our set S on a number line. And our first example is script F is the set of all open intervals of the form negative R to R, where R is a natural number. Again, so to be explicit, my indexing set here is the natural numbers. That's an infinite set, right? Countably infinite set. And for every natural number R, the corresponding open set is the open interval from negative R to R. And so if we were to draw this on this picture, we would see the following, right? So we would go ahead and we would see that the first one, when R is equal to 1, that is the open interval from negative 1 to 1. From when R is equal to 2, that's from negative 2 to 2. For 3, that's from negative 3 to 3, and so on. I'm sort of drawing these stacked on top of each other, but we can see how every open interval is contained in the one that came before it, or is contains the one that came before it. And in relatively short order, right? I'm not drawing this to scale, but in relatively short order, we would end up with sets that completely contain our set S. In particular, if I wanted, I could just take a single set, right? Maybe O sub, let's say O sub 1, right? So just a single set, one element in my set, and that's going to be the set from negative, I don't know, let's just say negative 15 to 15, right? So that is one set. It is one set that was an element of F, and yet it, from negative 15 to 15, completely covers S. So this particular infinite open cover of S admits a finite subcover. Specifically, it admits a finite subcover that contains just a single element, that contains just this one open set. Okay, great, and that's our first example. Okay, so for our second set, we have got the following. Our script F is all sets of the form x minus 1 to x indexed by the elements of S itself. All right, so that's sort of weird. Here our indexing set is the set S itself. Again, that's from 0, that's the entire half open, half closed interval from 0 to 10. And so there are uncountably infinitely many x values here. And for each of those x values, we are looking at the open set, the associated open set that starts at x minus 1 and that ends at, but does not include, the number x itself. So again, there are uncountably infinitely many of these. We won't be able to draw them all. But for example, when x is equal to 0, we get the corresponding set O sub 0, which goes from negative 1 to 0, not including 0 itself. If I were to plug in, for example, the number x equals 1, we would get the set from 0 up to 1, not including 1 itself. At the moment, 0 is in neither of these, but notice if I took the x corresponding to x equals 1/2, let's say, right? So if I took x equals 1/2, then the corresponding O sub 1/2 would indeed cover the point 0. And what we see ultimately is that even though there's uncountably infinitely many of these, I can sort of collect enough of them sort of staggered, right? So let's make sure this picture is clear. So I've grabbed, for example, O sub 1/2, O sub 1, O sub 1.5, O sub 2, O sub 2.5, O sub 3, and so on. I'm making sure that they overlap a tiny bit. I'm making sure that they're all elements of my original set. And I can end if I'd like. Remember, there is no O sub 10 because 10 is not an element of S itself. But if I chose, let's say, O sub 9.5, that would go from, let's see. Well, 9.5 would only go from 8.5 up to 9.5. So we end up in this kind of interesting situation where in order to cover everything up to 10, I'm going to have to include a lot of elements sort of up here, right? So I can't quite cover the number 10 itself, but I could cover the number 9.99, not with the open set O sub 9.99, but with the open set O sub 9.999. That would cover the point 9.9. Similarly, I could have another open set that's even closer to the edge, right? So you could have it right here. And maybe that's O sub 9.99999. And then I could create another one that's O sub 9.99999, and so on. And so I can create infinitely many I can select infinitely many open sets from F itself that will ultimately cover S. However, there is no finite subcover of this set F. There is no finite collection of these that will completely cover the set S. So S, let's say this correctly, F is an open cover of S, but it admits no finite subcover. So there is no way I can select finitely many of these elements and completely cover all of S. I would ultimately have to leave off something a little bit close to this endpoint here, 10. Let's look at one more example that I think makes this just a little bit clearer. Okay, so this is the open set, or this is the collection of open sets F, which are of the form -1 to X, such that X is an element of S. So once again, we're indexing by our set S. This time, all of my open covers have the same left endpoint. They all start at -1, but they go up to a certain point S, right? Or a certain point in S. So I could talk about O sub pi, right? And O sub pi would be the open interval from -1 up to pi, and so on and so on. Now, what we're going to see in this case, right? And I think this illustrates it even in a more clear manner than the one above. What we're going to see here is that this will ultimately, as an infinite set, cover everything in S. I can show that rigorously, right, by showing that for any value in S, so for any y in S, y is contained in the interval from -1 to, I don't know, let's say y plus 10 over 2, right? So to make that, and that would be the open set O sub y plus 10 over 2. Right, so what's happening there is if I choose any y value inside this interval, let's say that y is right here, right? And I want to know if y is contained in the infinite open cover. Well, it should be. Yeah, all I have to do is pick a number just a little bit above it, and that's why I picked y plus 10 over 2, right? That's going to be the halfway point between y and 10. Then the specific set O sub y plus 10 over 2 will be this set right here, right? That's O sub y plus 10 over 2. And that set necessarily, definitely contains the point y. So every y value in S is definitely contained in at least one of these open sets, and therefore this is an open cover for y. And yet, no finite subcover will completely cover all of S. So we're saying here, S is a subset of the infinite union over all x in S of the sets of the form -1 to x. Or alternatively, I could have written that as S is a subset of the union of all open sets in my complete open cover of O. Right, so either way, I'm saying here that S is contained in the total union of all of these sets, aka F covers S. All of those are equivalent and true statements, right? All the same, all correct. But what we're going to claim now is that F does not admit a finite subcover. And so to see this, we want to make the observation that if I only take finitely many of these open intervals, there will be a maximum open interval. There will be a largest open interval, right? And if I want to see it in terms of x values, if I take a finite list of these x values, there will have to be a largest x value. And so if there is a largest x value, right, let me erase some of this, right? If I were to take a finite collection of these with a largest x value, then I could just consider that largest x value, right? Maybe that's all the way up to here. Maybe this is the largest x value, but it will not get all the way up to 10, right? It will not get all the way up to 10 because 10 cannot be that largest x value. 10 is not contained in the set S. And so our x values cannot equal 10. So even if that largest x value was 9.9999, there would still be a little bit of space left over here. So because of that, we will say that that S, no, I said it correctly the first time, that F does not admit a finite subcover of S. All right, and so that's an interesting example. Our set S can have many, many, many different open covers. Some of them, like this first one, will admit an open finite subcover. Others, like this one, will not admit a finite subcover. And I think now we are ready to turn the page and look at this concept of compactness coming up in the next video.